what did I
as
say?
yes sir.
I did not get the statement. What did I say in the last class?
Sir, as you are telling us that we are having a discrete form of torque in a linear region, we are supposed to have the to operate in linear region.
Ah,
So, sir, this is because we are having dl by d theta equal to 0, or because we are exciting our current in a particular region. Because, sir, if we are exciting our current in a particular region, then due to inductance, we are not having a particular region current. It is some kind of declining, and sir, this is my question, sir.
I did not get your question. So what we are trying to do, basically, we are trying to get torque generated in the SRM. The SRM torque is generated in this manner. There is component of excitation which is coming as I square, which means it is not dependent on the direction in which you are giving the current. And then the rate of change of L with respect to theta. So if this is positive, then we are able to generate positive torque. If this is zero, whatever amount of excitation you give, you cannot generate any torque. If this is negative, you generate negative torque. So if you plot the inductance of this SRM, which is 2 by 2 single phase SRM, very, very basic SRM, starting from this flip position, theta equals to 0, where the inductance is minimum. So at 90-degree mechanical, it will reach the maximum and it will continue in that manner. Now what we are seeing over here is that there are only particularly two slopes which are visible. One is positive, another is negative for the inductance. This is basically zero slope. This is also zero slope. This is also zero slope. Practically, this is what we will encounter. Now, if you wish to generate, that is what is plotted over here also, dou L by dou theta. So there is positive slope only for certain range of theta. Then there is negative slope. Then there is positive slope. If you keep the excitation constant, then you are going to generate torque which will be pulsating, going positive and negative in nature, and thus the average torque will be zero. So instead of that, what we do, we apply the current only at certain places. For example, here or here or here, and then we generate only positive torque. Then the average torque is greater than zero.
Sir,
Similar thing.
yes,
Huh.
sir. Here is my question, sir. I here we cannot provide the current in a particular region.
Why?
Yesterday you told that we are using H bridge by using fast decay we can have, but sir, also due to fast decay we cannot have in particular region due to
Why?
inductance, sir, stator winding.
So what are we drawing over here? Are we not considering inductance when we are taking this current? So
Yes,
your
sir.
current will be zero initially. Let's say this case, what I have drawn over here. Let's say at this point you got the indication from speed encoder or position sensor that your theta has reached the point where you need to apply the current in this particular coil. Okay, say theta is some phi 1. It has reached here. Now you need to apply the current. So what you will do, you will change the mode to this 1 and then current will rise. And then you apply your hysteresis and keep the current within this band. So it can be done in the slow decay manner or fast decay manner. Both are okay. So you are able to maintain the current in this zone almost close to the mean value what is required for this duration of theta, whatever is needed. So what's the problem in this? Then you keep silent for some more time.
No, sir. Sir, we are matlab, we are I understand, sir. Sir, the instantaneous pickup that you are having is this line, that is the starting line uh, where you are pointing, sir.
Hmm. This will not happen in case of inductor.
Yes, sir, this will happen, sir.
Then
Sir, for some time then we give some break and then shift to other winding. to excite.
In between.
Yes, sir.
Why?
Sir, to have a particular region torque, linear region to operating.
Sampan, I think you are thoroughly confused. We have discussed the multi-phase winding, this multi-winding motor also, where we have, let's say, this kind of three-phase system. Do you see two currents overlapping? You are operating one current, it is starting, ending here. Then you have next current started, then you have next current started. That is how the windings are configured.
Yes, sir. Sir, now I get this is a RAM form. The square wave that you draw is a kind of ramp.
Of course, of course.
Yes, sir.
At least now you should be able to understand these things, right?
Yes, sir.
These are pretty obvious things. When you are drawing for a very large range of theta or time, a small ramp will look like a steep square wave only.
Yes, sir.
Okay. Any other doubt? So Deepak wanted to see yesterday some more than three-phase motor. So this is a kind of stator rotor configuration. I think this is five-phase motor. So let us count how many poles are there. 4, 5, 6, 7, 8, 9, 10. So this is 10 stator poles and then 12 rotor poles. So now this is a kind of SRM, a more practical SRM where you have 10 by 12 configuration, and let us see how many phases we are able to get. So one position with respect to this particular position of rotor, if we see that this is pole, these are the stator poles which are completely aligned with the rotor pole, correct? The another position, if you find, this is partially aligned here and here. Then some more positions which are like little further it is going. So this is another. Then one more place which is even more far from the rotor position. And then something which is going away, or you can say no, still more far, or whichever way you consider. So this is how we can have, let's say, phase 1, or let me write as ABCD. So this will be something like phase A. Then you can say this is phase B. This could be phase C. This could be phase D. And this could be phase E. You understand, right? With respect to the rotor position, at whatever point it is, you can see that two poles are coming similar. It's not necessary that only two have to be similar. There could be four also. If the machine is designed in a different manner, there could be four poles. So all four will be clubbed together as one phase, say A. The next one is, which is looking similar, is this, partially overlapping. So this can be grouped together and it can be called as B. There could be more. If they are looking similar, yes. Similar meaning if this is the direction of rotation, next this will go and align to that. The difference between this E and B is that B is going to align and E is moving away. So which is why these two phases are different. Again, difference between D and C is that after some time C will get aligned, whereas D will still take little more time to get aligned. This pole is only moving away from this stator pole. So that is how the different phases are grouped. You understand the point, Deepak? Am I audible?
Yes, sir.
Yes, sir.
Okay. Deepak, is it clear?
Yes, sir.
So this is what I meant by having grouping of the coils together. Whichever pole positions are looking similar, you group them together and make it as one phase. That is how you will be able to differentiate between different, how many phases are. So this is something like 5 phase 10 by 12 SRM. If you change, let us say, number of rotor poles, you may get little lesser number of phase for the same stator configuration. For example, you try 10 by 4 or 10 by 8, you will see that number of phases have changed, because it only depends on how this is getting aligned with respect to the rotor poles. So you can group all the phases together, which are, or all the poles together, which are coming in a similar position. Okay, so this is something like more practical, where we have more number of poles on stator and rotor. Now, if you see the step angle, how much it would be? 360 by ns, so 10 minus 360 by 12. How much this will be? Step size?
6 degree.
6
degree.
So this is what we are getting. Now 6 degrees, something like you are having more accuracy in your movement. You are turning at every 6 degree, which means if someone says that, okay, move exactly by 48 degree, or let us say some other multiple of this, so you can exactly move. 8 steps you have to take, or 10 steps you have to take. That accuracy is there. So in fact, the accuracy can be increased if you go for a situation where you try exciting the two coils together. Let's say A is excited already and you excite B also. With that, what will happen? What will happen? Now this is overlapping here completely. What is expected that when you close A and excite B, this will overlap completely. This is what is expected. But if you excite both together, what will happen? This will settle somewhere in the middle. So then you can make your step size as 3 degree. You can reduce it to half. This is the typical way how stepper motors are operated. Stepper motor, by the way, is combination of both the SRM plus BLDC, which means it has magnet also and it has the reluctance torque also. So to illustrate that little better, let us see. These are some of the techniques which are used by the industries to run their motor better. Okay, so I think this and this will make things clear. Okay, what I'm talking about is, say, first case. What we are doing? We are exciting A, then we are exciting B, again we are exciting A, then we are exciting B. That's the normal thing. Step size is 90 degree, it's moving, right? Fine. There is no problem in that. Now, try something like this. When you excite both A and B together, then there is tendency for the rotor to get aligned, it gets aligned between the two. Which means if you use both these things together, 4 steps over here and 4 steps over here, you can get something like this. You start with A, and instead of going to B directly, what you do? Next step, you excite both. So now this will move 45 degree. Then you switch off A, automatically it will go and align along B. Then you switch on A again. Again, it's turning only 45 degree. So what you have done? You have changed your step size or step angle from 90 degree to 45 degree. You understand my point? You understand this point?
Yes, sir.
Now I take this to another level. Now what we are doing, we are only exciting DC current for A and DC current for B. Now, why is it necessary to have a fixed value of current for rotating this motor? You can have something like, okay, I think that waveform is not given here. Just let me see where it is. It's very interesting actually. Yeah, this one. Now you see this. Why I need to have only DC value of current constant, no? Constant value of current. See what I was doing, I was exciting A, then I was exciting B, then I was exciting A again. Positive negative doesn't matter, right? But when it is having SRM plus BLDC configuration, then this direction also matters. So that's why it's taken as this. Now, instead of going at constant values, let's say you start reducing this slowly and start increasing this slowly in a sinusoidal fashion. Then what will happen? Your rotor will not just jump for 45 degree in the next step. It will slowly move from one position to another position. So now, whatever 45 degree you had, that is divided into so many steps. Whatever are the number of steps in this sine wave. So see, this is one example of running your stepper motor, or you can say SRM motor with sinusoidal supply, sinusoidal current. Somebody will ask, can you run SRM with sinusoidal current? So normally people will say, no, it's not required over there. But see, here we have. So possibility of everything is there, but we should know how to apply that. Do you understand this point? Do you understand this point or not?
Yes, sir. Yes, sir.
Okay, shall I close the
Yes,
SRM chapter here?
the speed will be slower in this case.
Yeah, then this frequency can
How
be,
will we determine the speed? Because
this frequency you can increase, right?
yes, sir.
This frequency will determine the speed.
Yes.
Correct? These are some of the things
Yes.
which are being used in companies like Texas Instruments or any other company which is dealing with this kind of motor drives. And these are all not very old. See, this is only 2020. They were about to give to the market that this is what is available. So some things which we feel that, okay, now there is no need of further research or no need of further thinking over this, but people come up with ideas which are really interesting. We need to keep our mind open. Am I fine?
Yes, sir.
Am I clear?
Yes, sir.
Okay. Any further questions? Fine. Okay, I'll close the chapter here. Now we talk about something which, let's say, we are more familiar with, kind of, you can say. Okay. So something like we have talked about the lumped winding motors or concentrated winding motors. Now we are trying to come up with model for, let us say, distributed winding motor. So one class of motor we have discussed, which is like SRM or real DC or stepper motor. These all kind of motors which are being run or which are being constructed using concentric winding, or you can say lumped winding. So they have pole which is basically having saliency and the winding is kept around that. This is one class of motor. Another class of motor what we know is basically where instead of having pole projections on the stator, we will have distributed winding which will be forming the pole in a little bit distributed manner. Correct. So example of these motors could be like induction motor, then PMSM, then wound rotor induction motor, so squirrel cage, wound rotor induction motor, and so on. So these motors are basically, these are having parameters, let's say inductance, resistance, and all that, which are linear, or you can say which are constant. These parameters are constant. So these motors basically form a linear system. So now we will learn how to control these motors in a better manner. So obviously two classifications for all these controllers we have seen. One is basically you have scalar control and another you have vector control. We all know from our previous understanding. So what is meaning of scalar control?
Only magnitude parity we can
Yes.
control.
So we are concerned about only magnitude of any quantity, let's say current. We are not worried or bothered about what is the angle, what it is taking or any other thing. It's just magnitude what is important over here. And normally we go for per phase based kind of implementation. Whereas vector control, as the name suggests, it deals with quantities which are vector, which means that there is certain magnitude associated with that and certain angle associated.
Direction. Yes.
Correct? So we are controlling both the magnitude as well as the angle. To have precise control over, let us say, speed or torque or any other quantity which you want to say position, any other thing. So we will now discuss. So under the scalar control, we have seen the direct online start for the induction motor, if I say. Then we have seen the rotor resistance insertion. Then we have seen V by F. All these methods we have seen, and we have found that V by F method is much superior compared to all. And this is universally accepted scalar control method for induction motor. Now in vector control, we are going to see something which is field oriented control. What is meaning of field orientation and what we are trying to control, that we will see in coming classes. Now first, when we are saying that vector control, we need to first know which vector quantity we are asking, or which vector quantity we are talking about, and how to express our voltage and current in terms of vector. This is the question. Ultimately, we are going to control this, but how to express our, and of course, we are talking about the multi-phase motors. So to start with, we can have three-phase motor. Now this three-phase motor we are trying to have in a manner that we can express the voltage, current, all these things in terms of vector quantity. So in space vector also we have seen during that lecture that if we have, let's say, three-phase system, we have voltages like VR, Vy, Vb. It can be expressed in a manner how we are distributing our windings and MMF and all that. So VR, Vy, Vb can be distributed like this. Only thing keep in your mind very clear is that these are forming stationary reference frame. When I am drawing VR, Vy, Vb, this axis, all three axes are basically coming in a reference frame which is stationary. This VR axis is not going to move. Vy axis is not going to move. And Vb axis is not going to move. This is not phasor what I am trying to draw. Correct?
Yes, sir.
So these are distributed in a space in this manner, any multi-phase system. And now particularly when we are dealing with machine, of course, we have windings which are distributed, which actually give us the representation like this. Now from this, when the three-phase voltage system is there, we can express all this as vector. This we have seen, right? So what we do basically, our voltage vector is nothing but VR plus Vy e raised to the power j 2 pi by 3 plus Vb e raised to the power j 4 pi by 3. I am taking this axis as my reference angle. So if this is my reference axis, then this is 2 pi by 3 and this is 4 pi by 3. You are free to take this also as reference axis, only add pi by 2. There is no problem in that. So just to make things convenient over here, I am keeping this as my reference axis. It is not theta equal to 0 position, but this is theta equal to 90-degree position. So just keep this thing in mind. Don't start theta equals 0 from here. This is only my reference axis. Then any vector, let us say representation of this Vy vector, representation of Vp vector, representation of Vr vector in this reference frame, that is what we have done. So in general, I have stated this earlier also. In general, if we have, say, this reference frame, any general reference frame where we have xy axis and we have a vector which is having magnitude of, say, I, and it is forming angle rho with the reference axis, then the representation for I vector is basically magnitude times of this. That is how mathematically we represent this unit vector e raised to the power j rho is nothing but giving the components of I along these axes. So I will write I cos rho plus j sin rho. So I cos rho is basically the component of I on this axis x. This is basically Ix, you can say. And then I sin rho is nothing but the component of I on this axis. So this you understand clearly, how we are representing the vector. So I can write this vector I as Ix plus jiy. So this underline basically means that the quantity is vector. Okay. So this is how we represent the vector in our course here. So don't miss this part. If I am writing any quantity as this, basically this is the unit vector which is giving its position, and this is the magnitude, or this is the quantity which is giving its magnitude, and it is expanded in this manner, and then it can be written in this form as the components. So Ix is nothing but I cos rho, Iy is nothing but I sin. Fine. We will be jumping between several reference frames. That's why it must be clear to all of you. Now, what we have. So similarly, when we are taking this as our reference axis, the Vr is sitting at 0 angle. So that's why I have written only Vr. It's e raised to the power j rho, j 0 degree. So which is nothing but 1. Now Vy, having magnitude of Vy, it is at a position 2 pi by 3 or at an angle 2 pi by 3 in the counterclockwise direction. Always remember, whatever we are measuring, the angle that must be measured in the direction which is counterclockwise. This is considered as positive angle. If you go clockwise, then it will be considered as negative angle. Fine. Definitions are clear?
Yes, sir.
So that is why Vy vector is represented like this. And Vb, which is again coming at 4 pi by 3 angle from this reference axis, is written like this. The magnitude is Vb and the angle is this. Unit vector is that, e raised to the power 4 pi by 3. Now it is up to us. We expand this, and we have seen in our class, previous class also, that this can be written as this. It is just expanded in this manner. So this is what we are seeing as two different components of this voltage vector V, which are basically orthogonal. Orthogonal means these two would not interact with each other. One is the real component, another is the imaginary component. So these orthogonal components are basically projections of this voltage vector on these axes. One which is along Vr, this is forming the real axis, also called as alpha, and another is the imaginary axis, also called as beta. So whatever components we have got over here, this real component is nothing but projection of Vs on this axis, real axis or alpha axis. This is called as V alpha, and the projection of Vs on the imaginary axis is basically V beta. So we can write the same vector Vs as V alpha plus JV beta. Because these three vectors are in a plane, so these can be represented ultimately as two independent components. Okay, in a plane we can have only two independent components which are orthogonal to each other. So where V alpha means what? Vr minus Vy by 2 minus Vb by 2, and if we have balanced system then it becomes 3 by 2 times of Vr. And V beta is basically root 3 by 2 times of Vy minus Vb. So these are the components of this voltage vector in this reference frame, which is called as alpha beta reference frame. And this is stationary reference frame, which means reference frame is not moving. This vector is rotating, which means what? After certain time, the voltage vector would be here. And so the projections of this vector on these axes will also change. The projections or the component V alpha B beta are dependent on time. And this is what we see also. If you expand VR, Vy, Vb in a balanced manner, you would find that this is coming out to be sine omega t, and this would come as minus 3 by 2 times of Vm cos omega t. So dependency on time is coming here as well. And that's the meaning. Vector is not having a fixed projection on this axis, but it is rotating. After some time it is here. So projection has changed. Now after some time it will move here, completely aligned along V beta. Then alpha will become 0. And that's the meaning of this expression, what we have got over here. Is that clear to all of you?
Yes, sir.
Now, this concept we are going to use to represent our model for these motors in terms of voltage and current vectors. So what we have basically, we are saying that we have cylindrical rotor machine, cylindrical rotor or symmetrical machine, you can say. When we have symmetrical machine, the meaning is that if we have three phase R, Y, B, these three phases are exactly identical. There is no difference in R or Y or B as such in terms of parameters, inductance, resistance or anything. Only these are distributed in space. So typically when we have, say, we talk about wound rotor, induction motor kind of generic structure, what we have three-phase supply given to stator, three-phase supply given to rotor. So altogether this forms like a dynamic transformer, which is basically rotating. So you have primary winding, you have the secondary winding, and for simplicity let us take 1:1 ratio for the number of turns. So this is what we are feeding from the stator side, the voltage Vs, and from the rotor side we are feeding the voltage Vy. We can have the dot convention also over here, and as a result of this supply we have current Is flowing into the, let's not give the vector as of now. The current flowing is Is and the current flowing here is IR. Now I have not said that which phase this is. It could be any phase. So that's why I will write I over here, where I is nothing but either R or Y or B. This is identical for all three phases. Per phase representation of machine, which is symmetrical. So only problem is that the rotor is rotating with certain speed, let's say omega R. That's the only difference between motor, AC motor and transformer. In transformer, we have both the windings stationary, the primary and secondary. Here we have rotor winding, which is basically moving at certain angle omega r. Is this clear?
Yes, sir.
Yes,
Yes, sir.
Good. Now, similar to transformer, what we have basically, we have the supply, voltage Vs, what we are feeding, and what components you expect in this winding. So there must be some resistance associated with this winding, correct? There must be some leakage associated with this winding, and because of this coupling, there must be some magnetizing inductance. Now, if we take this whole thing on the stator reference frame, what we will do? We will draw, because this is 1:1 ratio, so parameters will not change. But the supply and the current must now be expressed as what is seen in the stator reference frame. See, here we were feeding VR. VR voltage, IR current is there. Here I am writing VRS, IRS. I am dropping because it's common for all three phases. What is meaning of S is that how this quantity is seen from the stator reference frame. You understand my point? So this circuit, same circuit, can be seen from two reference frame. One reference frame, if you just sit on the stator. From the stator, what you would see, stator quantities will look as it is. There is no problem. But rotor quantities will look different. You understand my point?
Yes, sir.
If you
Yes,
want
sir.
to experience, just try sitting on the fan while it is running. So you see how your room is visible. It will look different, right?
Yes, sir.
What? Yes, sir. You tried sometime.
No, sir.
That's the same meaning over here. You are looking at the same quantity, but now what is happening that you are looking at something which is rotating. Now you are sitting in room and look at the fan. This is what is the stator reference frame. And you sit on the fan and look at the room. That is your rotor reference frame. So what will be your observation? In first case, your fan is rotating. Correct, right?
Yes.
So in first
Yes,
case, your rotor is rotating. In the second case, what will happen?
Room is rotating.
Yes. So from rotor point of view, stator will be rotating. It's only reference frame where you are sitting. There is no absolute stationary reference frame at all in this universe. No absolute stationary reference frame. Everything is moving. Everything is rotating in this universe. So there is no absolute stationary reference frame. It's only relative. If you are sitting on Earth, we are seeing everything with respect to Earth. Understanding my point? And by chance, our motor is sitting on Earth. So stator is attached to Earth, and that's why we are seeing that rotor is moving. If you disconnect all the couplings and all these things from the frame and put it somewhere in the universe and give the supply, both will rotate. You cannot say which is stator, which is rotator, which is rotor. You understand my point?
Yes, sir.
So which is why it is very, very important to write the superscript which indicates that which reference frame you are referring to. So these parameters, let us say, are same. RS, LLS, LM, LLR, RR. These are same, no problem. If turn ratio is 1:1, that's fine. If it's changing, then we will change these numbers also according to the turn ratio. That's fine. That's one thing. But the other thing which is coming only because of this rotation, that's what I'm trying to say over here. So this circuit what I have drawn is from the stator reference frame point of view. which is why the rotor quantities must be expressed in this reference frame properly if you want to write the equation. Otherwise, you cannot write. You understand my point, right? Do you understand or not?
Yes.
Yes, sir.
Yes, sir.
Now, if someone sits on the fan, which means they are seeing the word from the rotor reference frame. So what will happen? The rotor quantities will look as it is. VR will look as it is. IR will look as it is. These parameters are same. Now what will happen to stator voltage and current? Will it look same as what it was previously?
BSR,
No.
ISR.
Little louder.
It will be, sir,
No, sir.
BSR rotor reference.
So we will be representing our quantity, voltage or current in the rotor reference frame. Okay. Now this is slightly confusing. We have rotor reference frame, stator reference frame. We are using this subscript, that subscript and all, superscript and all that. How to differentiate that which reference frame we are talking about? So I give a generic name for this. I call something as native reference frame. You know what is native, right? What is native?
The near.
Not near, it's the home where it is. Let's say for you, your native or hometown or your home is at certain place. You are defined there in a different manner. When you come out, you take different definitions. So native is something like which is the natural or the home for that particular quantity. Let's say if I talk about rotor quantities IR and VR, what will be the native reference frame?
Rotor.
Rotor reference frame. And if I talk about VS and IS, what will be native reference frame?
Stator reference.
Stator. This point, do you understand?
Yes, sir.
What
Yes.
is meaning of native reference frame?
Yes, sir.
So see closely. When I am writing the quantity in its native reference frame, I am not using any superscript. It is written simply VSIS because I am talking about the native reference frame of this quantity, stator reference frame. Whenever the quantity is referred in any other reference frame other than its native, then I have superscript. There can be only one native reference frame for a quantity, right?
Yes, sir.
You cannot say something is having two native reference frames. That's not possible. So here if you see VR and IR are written as it is without any superscript because it's in their native reference frame. It's in the rotor reference frame, whereas VS and IS are written with superscript R. Fine. Do you have this clarity?
Yes, sir.
Yes, sir.
Yes, sir.
Now, one thing which you must understand very clearly after this point, whenever you are writing stator equation, you must write this in stator reference frame. We can transform it to another reference frame, that is fine. That's different thing. But when we are writing the stator equation, it must first be expressed in stator reference frame or its native reference frame. So every equation first we will write in its native reference frame. So if we are writing a stator electrical equation or stator KVL, that will be written in stator reference frame. If we are writing rotor KVL, we will be writing in rotor reference frame. You understand this point? Later on, we can transform. We can go from any reference frame to another reference frame. But this validity of this circuit, what you are drawing over here, is attached to which reference you are referring to, which reference you are defining in that. You understand my point?
Yes, sir.
Yes.
So now, if I have to write the stator KVL equation is only this part. Rotor KVL equation is only this part. What is consisting of stator supply, stator quantities, and the magnetizing inductance. That's all. Rotor is also what is rotor supply, rotor current, rotor parameters, and the magnetizing inductance. Magnetizing inductance is common. That's why it must come in both the places. Now, let us try to write this. You write Vs, okay, or let me take it here. So if you write stator equals, you have stator supply. I'm not writing RYB, so it is common for all three phases, right? Or let me write R for example, just to have this clarity. So ISR, which means I'm referring to R phase. RS plus LLS ddt of ISR plus LM times of ddt of. Now both the currents are entering in this magnetizing branch. IS is also entering and the rotor current referred in stator is also entering in this branch, right? That is how we represent. So both the currents will be visible in this term. So it will be ISR plus IRR in stator reference frame. I am going little slow because this is involving several fundamental things and a lot of references here and there. So ask if you have any doubt in this equation.
Sir,
Yes, Ashish.
sir, in PMSM, rotor is permanent magnet.
I'll come to that. First, what I'm having is this circuit, right? Don't jump. As of now, what you have this rotor, which say is wound rotor induction motor, where you can give supply on both the sides. You have current on both the sides. We will see how this can be taken for PMSM or anything else. We'll see that later on. But as of now, this is what we are having. Most generic form of any symmetrical machine. So, is this equation clear to all of you? Or any confusion in this?
This is with respect to rotor reference frame, right?
Which equation we are writing?
So
Ajay?
ISR.
R is R phase.
So my internet is very slow.
Then I think offline classes are very
Yes, sir.
necessary.
Yes.
That's why only Uday is remaining. Otherwise, I would have started. And of course, Deepak will also come on fourth. Because here, if you lose connectivity or these things, then you will miss very important thing here. Okay, this we are writing stator equation. So in which reference frame are we writing this?
Stator reference.
Yes, stator reference frame.
Now I will write rotor equation, rotor KVL. So which reference frame it should be?
The rotor reference frame, native.
Rotor
native.
reference frame. So which means that we are referring to this circuit where we have VR, IR written as it is without any superscript. So what I will have, VR, say I'm talking about R phase, IRR, RR plus LLR DDT of IRR plus LM DDT. Again, now both the currents would enter in this magnetizing branch also. Correct?
Yes, sir.
Right? So that is why both the currents should be mentioned in this with this LM branch, the magnetizing branch. So what this will be? This will be ISR, but in the rotor reference frame, because we are writing rotor equation, and then IRR as it is without any superscript. So we have written this rotor equation in rotor reference frame. You understand my point?
Yes, sir.
Yes, sir.
Just
Yes, sir.
analogy I will give what I am meaning by referring this and that to different frame. This no reference frame is that, let's say all of you are in IIT Roorkee. You don't address each other by saying that, hey, I am so and so from IIT Roorkee, right? Because it is well known, you are students over here. But once you step out of IIT Roorkee, you will be referring yourself in a different manner. I am so and so from IIT Roorkee. Your way of defining yourself has changed. That's the meaning of this. Any quantity, when you are seeing it in its native reference frame, it doesn't need any further description. It's the current, it's the voltage. But the moment you step into another reference frame, you have to have some other way of saying that. You understand this point? Now,
Yes,
how
sir.
to define or how to get this? Because these are not the simple measurements, right? This is referred to stator or referred to rotor. How to get these numbers, that is what we will see in the next class. And then we will proceed towards the modeling of PMSM and the squirrel cage induction motor from the same understanding. That's why I'm putting everything in generic form. What is the maximum possibility what we can have? At the most, we can have supply on both the sides, stator as well as rotor. Now, squirrel cage will not have supply on the rotor side. PMSM will not have any circuit on the rotor side. So these are special cases of what I'm discussing over here. If you are able to understand this, then other things are easier. Am I clear?
Yes,
Yes,
sir.
sir.
Yes,
Okay.
sir.
Try
Yes,
to think about this a little bit more, and if you have any quick questions,